Okay, in this video, we're going to take a look at rotational non-equilibrium. And this is just going to be a case study of a specific example of a disk which is rolling down a ramp. Now, the reason I'm doing this case study is because there, there are two primary ways of solving this problem, of looking at the problem. And I want to make sure that it's perfectly clear to you how it's done, and because I don't want there to be any confusion, because I know many of you will go out on the internet and you'll look to see what other people are doing to try to help you with specific types of problems. And so I think it's important to take the time to show you what I'm about to show you. So the first thing I'm going to do is start this off with a question. And the scenario is that we have a disk which is placed at the top of a ramp, and that disk is going to roll down the ramp. And ultimately, what we want to know is what is the acceleration of the disk as it goes down the ramp. So my question for you is, what do we use for the axis of rotation? I think it's pretty clear that the disk appears to be rolling around this point of the center of mass. However, you may also consider that this point of contact is also going to be the axis of rotation. And so my question for you is quite simply, which of these 2 points is the axis of rotation? Okay, so the correct answer, they are both the axis of rotation. Why? Because the axis of rotation is arbitrary. We can put it anywhere we want. Now, typically in a college level or algebra-based physics course, the axis of rotation is placed at the center of mass. That would be this point right here, the one at the center of the disk. And that's because when it's at the center of mass, we don't have to use the parallel axis theorem. But if we pick this point on the bottom, then we have what would appear to be a completely whole other step. And so we're just going to go through this using both points for axes of rotation so that it's completely clear to you how this actually works. Okay, so the first thing you have to do anytime you're solving a force problem is draw your FBD. And remember that when it comes to extended objects, the FBD, the forces on your FBD must be located where they're physically located on the object, at that point of action. Now, the disk has a radius of r, which I'm going to label here. So there's the radius of our disk. And the actual forces for our disk are going to be the normal force, which starts at the point of contact and actually passes through the center of mass and points in this direction. We have the force of gravity, which originates at the center of mass and points in the down direction. And then we have the friction force, which originates at the point of contact and points parallel to and up the ramp. So these are the 3 forces which are acting on the disk. So this becomes the normal force, force of gravity, and the friction force. Okay, so now let's go ahead and solve this. We have tau net is equal to I alpha, that's normal. And then we've got 3 different forces, and we're going to do all 3 of those forces as torques. That way we don't overlook anything, because there's so many small things that can go wrong in these problems. So we have the torque due to the normal force, plus the torque due to gravity, plus the torque due to the friction force is equal to I times alpha. Now let's redefine our torques using our definitions, and then we will look at each variable one at a time. That's important to not missing anything. So we have R for the normal force, F normal times the sine of phi normal, plus R gravity, F gravity times the sine of phi for gravity, plus R friction, F friction times phi for friction. And that's going to be equal to I alpha. So we're first going to use the center of mass as the axis of rotation. So this is going to be using the CM as the axis of rotation. All right, now R for the normal force is going to be from the axis of rotation, which is the center of the disk, down to the point of contact. And so if we draw a new vector for that, this is what R would be right here. Okay, so that's going to be R for the normal force. That is non-zero, so that's just going to be R. And then we have the normal force, and then we have the sine of phi. So what is phi? Well, remember that we're going to take our two vectors and place them tail to tail. So we have the normal force points in this direction, and then we have R points in that direction, and the angle here is 180 degrees. So phi is 180, but the sine of 180 is 0. So what that means is this whole term is going to go to 0. Sine of phi is 0. So good, we've eliminated one of our torques. That's like awesome sauce. Okay, so now let's go ahead and move on to gravity. Well, the force of gravity originates at the axis of rotation, so right away we can see that gravity has 0 R, so the torque due to gravity is going to be 0. So all that leaves us with is R for friction, which it's easy to see that friction is going to have the same exact R as the normal force because it starts at the axis of rotation and goes to where the disc touches the ramp. And so we have R, and then the force of friction. And I think it's also easy to see here that this is a 90-degree angle. Okay, so the sine of phi, that should be the sine of phi, this is all going to go to 1. So we just have R the disk times the force of friction is equal to I alpha. Okay, so let's continue on. We have R times the force of friction. The moment of inertia for a disk, if you recall from a prior video, you could even look this up in a table, but we get I is equal to 1/2 mr squared. And then finally, because we're looking for tangential acceleration, or the acceleration of the center of mass, I'll call this ACM. Because we're looking for the acceleration of the center of mass, we've got to convert alpha. And alpha, we'll use a bridge equation. A is equal to alpha r. So alpha is equal to A over r. And so we get A over r for alpha. And now we can eliminate this r cancels with that r, and this r cancels with that r. And so finally we're left with the force of friction is equal to 1/2 ma. But don't be fooled. Okay, it's real tempting to want to take friction and do this with it, right? You're going to want to do the force of friction is equal to mu times the normal force. And you don't want to do that. You can, it's just it's going to complicate the algebra a little bit. So we're going to not do that extra step. And so then you might be asking, well, then what do we do? And the answer to that question is we're going to use Newton's second law for translation, because guess what? this disk is still translating through space, and Newton's second law is still going to be valid. So in order to eliminate friction, we're going to do this. We're going to write F net is equal to ma, and when you look at the FBD for F net equals ma, what we get is, if we draw our FBD here very quickly, we have the force of friction points up the ramp, and the force of gravity parallel points down the ramp. And so we can write the force of friction minus Fg parallel is equal to a minus ma, because it's accelerating down the ramp. All right, so the force of friction is just equal to Fg sine theta minus ma. And so that's what we'll put in for our force of friction. And so we get Fg sine of theta minus ma is equal to 1/2 ma. And now we're trying to isolate a, so we'll just put a to the other side, and we'll rewrite Fg in terms of the mass. And so we'll get mg sine theta is equal to ma plus 1/2 ma. And now to get a by itself, we factor it out. And so we're going to get mg sine of theta is equal to, or actually we could just do it this way, ma plus 1/2 ma would be 3/2 ma. And then mass cancels out, and so we get 2/3 g sine of theta is equal to the acceleration. So that is our final answer for the acceleration of this disk. Okay, so that's method one. That's using the center of mass as our axis of rotation. But what happens if we don't use the center of mass as our axis of rotation, but we use the point of contact as the axis of rotation? Okay, so try to use the point of contact as the axis of rotation. Try it on your own and see if you come up with the same answer, and then we're going to do it together. Okay, so I'm just going to quickly sketch out our drawing once again. We had our disk, our ramp, and then we had the normal force pointed in that direction, the friction force was in that direction, and our force of gravity comes from the center of the disk and it points down. And so we're going to start our problem the same way we did it before, and we're going to start with tau net is equal to I alpha, and tau net is going to be all three of these forces put into one equation. So we have the torque due to friction is positive because it's making a counterclockwise rotation. Then we have plus the torque due to the normal force plus the torque due to gravity is equal to I times alpha. So this becomes R friction, F friction, sine of phi for friction, plus R normal, F normal, sine of phi for normal, plus R gravity, F gravity, sine of phi for gravity is equal to I alpha. Okay, now R, remember, goes from the axis of rotation to where the force is located. If this is going to be our axis of rotation, then the force of friction and the normal force both have a 0 R. And so that means this is 0 and this is, wrong one. This one is 0. So we can eliminate these two terms, and that's just going to leave us with R gravity, F gravity, sine of phi for gravity is equal to I alpha. Okay, so what we're going to do is we're going to, remember r is going to be this for gravity. So this is r. And we're going to place our two vectors tail to tail, and we have the force of gravity points straight down, and r points like this, and we'll just say this is an angle theta right here. That's typical for ramps. And the angle we're interested in for phi is this. So you can go through the geometry of it. Okay, if this is our ramp here, you know that this is going to be 90, and you know that this is going to be theta, so this is going to be the complement of theta, and it starts to get a little bit ugly. But what we know is this: the r vector is perpendicular to the ramp. And so what we really need to do this, because remember, torque, we said, could be defined as r perpendicular to F, or torque is r times the force perpendicular to it. Okay, so we just need the components of one or the other, which is perpendicular to the other. And in this case, r is perpendicular to the ramp, and we know from doing ramp problems in the past that the force of gravity parallel, this would be the force of gravity perpendicular, and that causes the normal force, but then we have the force of gravity parallel, and that's what caused boxes to slide down the ramp. Okay, so we're going to have Fg parallel is perpendicular to r, and so what we're going to write is that the torque is going to be equal to r times Fg parallel, and then we can ignore the sign of phi. So this is just going to go away because we're going to write this as Rg times Fg parallel is equal to I alpha. Okay, so finishing this up very quickly now, what we have is r times Fg sine of theta is equal to I for a disk, which is 1/2 mr squared times alpha. And remember, we want to convert that into translational variables, and so alpha was equal to a over r, just like before. And so we get r times mg sine of theta is equal to 1/2 mr squared a over r. Now, did you pick up on the mistake? I hope you did. Okay, I pranked you. Remember that this is the moment of inertia through the center of mass. So this line doesn't work. We've actually got to do some more work here. Okay, so let's do that. Let's get rid of that so that you don't see it. But let's do the parallel axis theorem to get I through the center of mass, or through the point of contact. So we know the parallel axis theorem is I nu is equal to ICM plus MD squared. And so in this example, our axis starts, well, the ICM goes through the center of mass, and we're putting our axis down on the edge of the disk. So D becomes an R. D is equal to R. So we have I is equal to 1/2 mr squared plus mr squared. And so I is equal to 3/2 mr squared. And that's what we're going to put into our equation. So we have 3/2 mr squared a over r. We'll cancel this r with that r, this one with that one, that mass with that mass, and by now I think you could probably see we have the same result. So cleaning this up, we have g sine theta is equal to 3/2 a, so that a is equal to 2/3 g sine theta, which is exactly what we had in the prior part of our problem. up above. It was 2/3 g sine theta. If I take you up there, you can see there it is. 2/3 g sine theta, 2/3 g sine theta. And so, just as a very quick recap, whenever we do non-equilibrium for Newton's second law in rotation, oftentimes we have to include either the parallel axis theorem or Newton's second law for rotation or translation, F net equals ma, and sometimes we just might have to do both or all three of those things.